Hey everybody, it's Mrs. Hofferberth. Let's talk about acids, bases, and the pH scale. Let's take a look at two lists of chemicals. The one on the left is a list of acids, and the one on the right is a list of bases. The first thing I want you to be able to do is look at chemical formulas and see the pattern that allows us to identify, is this an acid or is this a base? So stop and look at all of the acids. What do they all have in common? Hopefully you notice that they all have a hydrogen written out front. This is an easy way to communicate to someone that the chemical you're working with is an acid. So you'll recognize an acid, in our context at least, by the fact that it has a hydrogen at the front of its formula. If you look at the bases, you'll see that they have something different in common. Every base has an OH in it. All of these bases have hydroxide. And so you'll recognize a base by the fact that it has an OH in it. So what is it that makes this hydrogen or this hydroxide cause a chemical to be either an acid or a base? It turns out that what's going on in an acid is that hydrogen that's part of the acid formula, that hydrogen can be lost to the water. And so when you put an acid in water, it is going to dissociate. The hydrogen is going to fall off. Dissociate means to break apart. That hydrogen is going to dissociate and actually attach itself to the water. And so if we take something like HCl, which is hydrochloric acid, and we put it in water, so that the left side of our equation is HCl plus H2O, this hydrogen right here is actually going to go and join the H2O, and you will make H3O plus and Cl minus. Now, when the hydrogen leaves, it does not take its electrons behind. Because it has lost an electron, it is now positive, and what it used to be attached to, the Cl, has gained that electron and is now negative. This H3O plus has a special name. It's a very special polyatomic ion. This is called hydronium. And what makes an acid, by the Arrhenius definition, there's actually 3 different definitions for acids. We're going to focus with the Arrhenius definition here today. According to the Arrhenius definition of an acid will increase the concentration of hydronium in solution. In this case, the hydronium is made as a result of this chemical reaction. Similarly, if you were to take acetic acid, which is the acid at the top of this list, that's what's in vinegar, you can write a similar reaction. Once again, you take the hydrogen that was at the front and you tack it onto that water and you form hydronium. And then whatever the hydrogen was attached to, the rest of that is written down, and now it has a negative charge. So this is the acetate polyatomic ion that you're supposed to know. So acids will react with water, you'll write them both in the chemical equation, to produce hydronium and a negatively charged anion. If you have an acid like H2SO4 that has 2 hydrogens on it, each of those hydrogens will go and find a water to attach to. And so if I write the equation for the dissociation of H2SO4, which is sulfuric acid in water, you will make 2 hydronium ions. And the SO4, now since it lost 2 H pluses, will have a negative 2 charge. But again, in all cases, the hydrogens that are written at the front of the formula, those are the ones that are available to be lost with the nomenclature that we are using. Each hydrogen will find its own water to form a hydronium ion. Bases are a bit different. They will dissociate to form hydroxide ions, another polyatomic ion you're supposed to know. Now it turns out that this only happens when you put them in water. However, the water itself doesn't change, it just separates the ions, and since the water is not changing, we typically do not write water in the chemical equation for the dissociation of bases. Instead, what we focus it on is, here is our starting base, say in this case sodium hydroxide. It is going to form sodium ions and hydroxide ions. So all we do for bases is we break our base apart. For our hydroxide containing bases at least. We just separate it into its pieces. The second one on the list, calcium hydroxide, you'll notice it had 2 hydroxides in the formula. And so when you write its dissociation equation, you get 2 hydroxides, 2 OH minuses. And then calcium has that +2 charge we would expect from the periodic table and its valence configuration. There is a special situation that I want to point out, and this is a common everyday base known as ammonia. You have it in things like Windex. Ammonia has the formula NH3. Now, if you look at NH3, you think to yourself, there's no hydroxide there. How is this a base? This is the one base that we are going to talk about in this class, where you do have to write water, because it turns out that ammonia reacts with water to form the ammonium polyatomic ion, another polyatomic ion you're supposed to remember. And when it breaks the water and takes the hydrogen off of the water, it generates hydroxide. And so it is creating hydroxide when it reacts. And thus it is a base, because by the Arrhenius definition of a base increases the concentration of hydroxide. In general, if your base already has hydroxide in it, you don't need to add water to the equation. If it's ammonia, NH3, you do need to add water for this special case. We just said that an acid increases the concentration of hydronium, whereas a base increases the concentration of hydroxide. This gives us another way, other than just looking at the formulas, to figure out whether a solution is acidic, basic, or neutral. We can look at the relative amounts of hydronium and hydroxide in solution. It turns out that they're related. There's really cool chemistry here. We're not going to have a chance to go into it this year. We're just going to take the results of that awesome chemistry. But what that chemistry tells us is that if we multiply the concentration of hydronium ions in moles per liter, molarity, by the concentration of hydroxide ions, we always get a constant. We get the value 1.0 times 10 to the negative 14th. What this means is that if we were to increase the concentration of hydronium, then the concentration of hydroxide would have to go down to compensate for that. On the other hand, if we were to decrease the concentration of hydronium, the concentration of hydroxide, again, would need to rise to compensate. Because they always have to multiply to give the same value, if one goes up, the other one has to go down. So in a neutral solution, the concentration of hydronium and the concentration of hydroxide are indeed equal to one another. On the other hand, if we increase the concentration of hydronium by adding an Arrhenius acid, we have to decrease the concentration of hydroxide, which means that in an acid, the concentration of hydronium will be larger than the concentration of hydroxide. And alternatively, if the concentration of hydronium goes down, the concentration of hydroxide will go up. And so that is a basic solution. In a base, the concentration of hydroxide is greater than the concentration of hydronium. Let me show you what this might look like in a problem. If we have a solution that has a hydronium ion concentration of 6.1 times 10 to the negative 12th molar and a hydroxide ion concentration of 1.6 times 10 to the negative 3rd molar, is this acidic, basic, or neutral? What we're going to do is look at these numbers and decide which one's bigger. Hydroxide at 1.61 times 10 to the negative 3rd molar is the larger value. Since hydroxide is greater than hydronium, this is a base. A third way we can determine whether a liquid is acidic, basic, or neutral is by measuring its pH. And this you might remember from middle school because you learned about it then. The pH scale is a way that we can test and measure a liquid to determine whether it is an acid or a base. And we can do this measurement either using pH paper, that's the colored paper that you dipped into the liquid and it changed colors into blue or red or orange, or using a pH meter, which will give you a number for the pH. The pH scale is convenient because it's consistent. It's something that's very commonly used, and it uses kind of everyday numbers, generally 0 to 14, to express how acidic or how basic a liquid is. At room temperature, the pH of 7.00, exactly 7, that is considered neutral. Something is neither an acid nor a base. On the other hand, if you have a liquid whose pH is less than 7, this is an acid. Most things you're going to come across will have a pH between 0 and 7. You actually can have a negative pH when things are very, very acidic. It's just less common to encounter. On the other hand, if you don't have an acid, you have a base, and those things have a pH that is greater than 7. So when you're talking about pH, things that have a pH, say, of 6.2, that's an acid. On the other hand, if something has a pH, say, of 12.7, that's a base. If something has a pH of 7.2, that's still a base. It's only slightly basic, but it is still a base. So pH of 7 is neutral, less than that is acidic, more than that is basic. Well, what is it we're measuring with a pH scale? How does that relate to the hydronium and hydroxide ions that we're talking about in terms of chemical structure? It turns out that the definition of pH is that pH is equal to the negative log of the concentration of hydronium ions in solution. So as we look at this equation I just wrote down, you'll be asked to use it. pH is just a number. Negative log, this is the logarithm button on your calculator. Every calculator is a little bit different. If you have a TI-30, the logarithm button is up here just underneath the second button. If you have a TI-83 or a TI-84, it is off to the left of the number pad. And if you are using the calculator on, say, the computer, on the browser, it's going to be off to the left of a scientific calculator, off to the left of the keypad. So you'll need that log button. And what you're going to do is simply type in negative, hit the log button, and then type in the value you're given for the concentration of the hydronium ions in solution. The larger that value for the concentration of hydronium ions are, the smaller the pH is going to be. So the greater the hydronium ion concentration, the lower the pH will be because of the math associated with this equation. And as I write this, I'm reminded that you may not have seen the square brackets before. These square brackets that I have around H3O+ here and here, that is a shorthand and it means the concentration. So if you want to calculate pH, you can take the negative log of that value. For example, we can calculate the pH of a solution with a hydronium ion concentration of 2.4 times 10 to the negative 8th molar. What I'm going to put into my calculator is exactly what I'm going to write down here on the screen. The negative log of 2.4 times 10 to the negative 8th. I want you right now to grab a calculator and type this in to make sure that you get the same answer that I do. You should get 7.62. Okay, really it's 7.169788758. But for sanity's sake, we are just going to report our pHs out to the hundredths place and stop there. If you tried this in your calculator and did not get this value, there's something weird about the way you're putting it in your calculator, and I encourage you to try again. And if it doesn't work, come and talk to me so we can get you sorted out. We can also work backward. If we know the pH, we can determine the hydronium ion concentration. And so the opposite mathematical equation is that the hydronium ion concentration is equal to 10 to the negative pH. Let's work an example so you can see how this equation works. In this case, our goal is to calculate the hydronium ion concentration of something with a pH of 3.65. Now 3.65, I already know it's acidic because it's less than 7. The hydronium ion concentration is going to be 10 to the negative 3.65. Don't forget the negative sign. And so you're going to grab your calculator, you're going to type in 10. You can finally use that caret button. So 10 caret negative 3.65. You should get the value 2.2 times 10 to the negative 4th. It may also be written on your calculator as 0.00022. Those are the same numbers. Now this is a concentration. You need to remember to put units on it. So these are going to be molar for each of these. So there are 3 different ways that you can look to determine whether a solution will be acidic, basic, or neutral. You can look at what the formula of the chemicals are in there. If there's a hydrogen at the front, it's an acid. If there's a hydroxide going on, or it is NH3, it's a base. You can look at the relative concentrations of hydronium and hydroxide. If you have more hydronium, it is going to be an acid. If you have more hydroxide, it is going to be a base. Equal amounts, it's neutral. You can also look at the pH, and you can either just be told the pH directly, or you can calculate it from the hydronium ion concentration. But if your pH is less than 7, it is acidic. More than 7, it is basic. And right at 7, it is neutral.